So it's my pleasure to welcome Cezara Dragoi. Cezara is now at INRIA Paris. Before that, she was a postdoc with Tom Hensinger at IST Austria. And before that, got her PhD with Ahmed Boujani, right? And she's done a lot of interesting work on verification and on reasoning about distributed protocols. And today, she will tell us a little bit about this. So go ahead.
Okay, thanks for inviting me. And thanks for being here on such a lovely Saturday afternoon. So yeah, this is joint work. It started while I was a postdoc in Tom's group, where I met Damien Zoufret, who's now at MPI Kaiserslautern, and Josef Wieder, who's at Technical University of Vienna. So we are interested in automated verification. And we are always looking for new domains where we can apply our techniques. In particular, we are interested in static analysis and in push-button methods, like those that are based on abstract interpretation. So we have looked at the domain of replicated state machines, and I'm going to explain a little bit. I'm going to start by explaining a little bit the domain that we are focusing on. And what we wanted to do was to design, ideally, push-button methods, more practically to understand what part of these implementations we can automate. So for which of this implementation we can generate invariants and like automate horse-style reasoning for those that are familiar with. And when we looked at this implementation, we were like, okay, they are very, very complicated. Just by, starting with like, there's a bunch of work done for static analysis in the sequential world. And just by, we can't just use on-the-shelf tools like that and apply it to this. So that's where the programming abstractions come into play. So let me start by telling you about replicated state machine. So typically, right, you have one server, one process, and you send requests to it, or you communicate, you have your application running, and as long as the processor doesn't crash, you're happy. But when it crashes, you're no longer happy. So if you're in the distributed world, to deal with this type of failures, what are you going to do? You're going to replicate your system. You're going to have several processes. And in case one of them fails, you're going to have the same application running on different ones. And then you're happy. But what you have to ensure is that you really have the same application. That on all your copies, you are actually running the same application, and your application is in the same state over the entire system. So let me get a little bit more specific. So I have here an example with 3 servers, and they receive requests. Requests can be anything. You can think of it if this is a counter, distributed counter, the A, E, B, C, D are going to be like increment, decrement, so on and so forth. But in general, these are requests coming from the client, and clients can send their requests to different replicas, and now replicas, they have to react. So in what we would call a strong consistent system, replicas are going to apply the requests locally. They are going to propagate all over the system the request, and only afterwards they are going to treat the next request, maybe from a different server or from the same one. These are strong consistent systems because every time you're going to query one of the replicas, all of them, independent of which replica you're going to query, you're going to get the same result. Just to make a little bit of a difference with maybe what you have heard of eventually consistent systems, these will be systems in which one replica, it's going to apply the request locally. It's going to propagate the request all over the network, but is not in charge of whether those messages were delivered or not. So in these systems, the systems might diverge, while in a strong consistent system, it's never diverging. These are very useful applications of strong consistency. Even if we understand exactly what it means, it doesn't make it easier. And it is applicable. So I have a few examples here, like Zab. It is a strong consistent, it's implementation of consensus that it's used by Zookeeper, which is a very, very used tool. Even Rupak mentioned it today this morning in his talk, so I'm not going to insist. ViewStamp is also one of the old replication state machine algorithms that it's used in distributed file systems. And Paxos, I think most of you have heard about it. It's used all over the place, from Amazon to Microsoft, so on and so forth. Okay, so this is the domain of application. So we are interested in implementation of replicated state machines. So we are interested in implementation of data centers that want to ensure strong consistency, and we want to develop techniques that verify them automatically. And with that, I even stated my goal. Okay, why is it difficult? There are two main problems. First of all, it has been shown, either you call it the FLP result or the CAP theorem, that you cannot have strong consistency in a network where you have faults or where you have partition. So you are either having availability, but you don't have a network partition, or if your network is partitioned, or if one of the processes crashes, you cannot solve consensus. So because of this fundamental theoretical result, people, I'm talking now about the algorithms community, I'm not yet at the implementation. So already theoretically, people have developed a lot of algorithms. Each of them try to try to come across this limitation by imposing different network restrictions. Like typically you will read things like, if n over 2 processes don't crash, where n is the size of the network, or if my network is synchronous. So then, you have the world of your networks and you design algorithms, each of them specific for one type of network. Then when you want to implement these algorithms, let's see what happens over there. So typically, these are using a synchronous parallel composition. What does it mean? It means that each process is seen as an individual. And the programmer needs to define very well what happens, what are the steps that the process goes through. And of course, you are familiar with the interleaving problem, with the explosion, and so on and so forth. But in this case, it's even more difficult because the steps are very, very small, and there are many things happening constantly. The process needs to react to many, many things. So the interleaving problem is really becoming challenging. Processes communicate via messages. In an asynchronous network, we do not know how long it takes for a message to be delivered. So if this process waits for message A1, it might receive B2 before. So how long it should wait for A1? It doesn't know. So then all of a sudden you have timer constraints. Moreover, you might still wait for A1, but you keep on receiving B2, B3, C3, so on and so forth. What should you do with those ones? Should I drop them? Will they be useful later? Let me put them in a buffer. Further on, the first 4 bullets, they didn't talk about crashes. Now, if you have processes that crash, in an asynchronous system, you cannot distinguish between a message that has been dropped by the network or never sent by the process that wanted to send it, or it's just like you don't know how long you have to wait for it. So you might still have to wait for it longer, or it's lost. So now when you have to deal with faults, people start implementing all sorts of problems, all sorts of techniques, like, failure detectors, like, okay, I'm going to do a parallel thing, like, okay, now I'm going to suspect process B, it's crashed, so I'm no longer waiting for messages for this one, so on and so forth. So all that makes the control structure of these implementations extremely challenging. So for the verification, right, you have messages, you have buffers, you have asynchronous parallel composition, there are infinite state systems, but they're really the worst ones you can imagine. So the verification is completely undecidable. So, okay, we have these systems. They are complicated to implement. They are complicated to design from the algorithm perspective, but we need them. Okay, I'm gonna, before going to my, to our results, I'm gonna talk a little bit what has been done in this field. The verification of this algorithm started quite recently. Like it's after the year 2010. And there are like mechanized approaches and like more automated ones. On the mechanized approaches, I'm gonna there is a very nice project, Verdi, and there's also EventML. So they are both doing mechanized proofs of the systems. What's nice about them is that they also, they start with a high-level specification and they generate code For example, Verdi uses Coq to generate OCaml code. So then they actually derived a proofed implementation, a correct implementation. But the drawback is that their implementations are really not competitive. They are extremely slow. Ironflea designed, so it's developed by Microsoft Research, and they do mechanized verification, but what they do, they have verified their own implementation of a distributed key value store. So it is mechanized, but it's verifying an actual implementation. TLA Plus, it's mechanized, but it's just doing specification verification, so there's no code. On the automated side, there are model checking techniques for protocols mainly that work just for simple protocols. There's the project that Sharon mentioned before, Ivy, that does verification of protocols with like more and more automation. And there's our approach that I'm going to talk about it in the next slide. So our approach was like, we want to use as much as possible from the abstract domains, from the decision procedures that have been developed for in the sequential world. So our main problem is this completely crazy control structure that arises from all sorts of places. So then what we wanted to say is like, isn't it there a better programming abstraction? Can we just structure a little bit this code differently? Can we have a different look over this code? And maybe looking at the same code with a different perspective, then we will be able to actually automate the verification procedure and synthesize those invariants automatically. So let me start by giving a brief example. So why is it so complicated? So here I have an example. Forget for a second about this part, sorry about the animations. I have a very, very silly example. So I want to solve consensus. So I want everybody to see, so there's one process that receives the request A, it's the green one here, and it wants to propagate this message through the entire network. Well, in this case, what is it gonna do? Well, first it's gonna send it to everybody, right? Then it's gonna wait for acknowledgement because it wants to make sure that everybody received the answer, right? The acknowledge phase. And then finally, when it knows that everybody received the command, it's gonna tell them, okay, now you can write it to your memory, to your log, or to your whatever, because now I am sure this is a well-established command. Well, right? This is very simple. And then you keep on doing this, that's all. But now what do you need from your network when you do this? Well, you are basically assuming synchronous communication. And in one way, and one way of seeing it is that you assume synchronous communication and no faults, right? And every message is delivered. Another way of seeing this assumption is that you have a leader, and everybody hears from this leader, receives the messages sent by this leader, and that also the leader receives all the messages that are sent to it. Whatever the replicas, the other ones communicate between them, it's not important for this protocol. So now if I'm using this assumption, I have a dissociation between what a replica is doing with the messages it receives. In this case, it's just storing. A similar view you would have in Paxos, where you would solve a little bit more complicated algorithmic problems. And what is the algorithm relying from the network? What is the algorithm does it need from the network? So right, if you see this as network assumptions, that the leader receives the messages from everybody, then you can think about how to implement them. And then you have like different ways of implementing it. So the fact that every process hears from the leader, you can implement it by just making the leader wait longer, increase your timeout. You can start sending heartbeats, hey, are you still there? Hey, are you still there? Or you can just say, okay, I'm gonna change the leader. This one is not replying to me anymore. So all these three are different ways of implementing something that has nothing to do with the computation that nodes do locally. It's just about a communication. Similarly, the fact that the leader hears from all processes, you can implement it in a similar way, with the exception that, okay, since the leader is waiting, if he doesn't receive messages from everybody, it's just going to commit suicide. It's like, I don't have a group P, so I'm going to give up. So what we noticed is that all these protocols, we need to separate the algorithm, or what we call the algorithm, what a process locally does with the set of messages it receives from what needs it has from the network on which it's run, it's executed. So this is what we call separating the network properties from the algorithmic computation. So when we looked at, okay, we are not the first ones, right? Distributed algorithms exist in the world for a long time. And the community came up with a lot of models. And we were searching the literature. So we were looking for something that separates the algorithmic computation from the network requirements. Since anyway, in reality, when we implement, we cannot distinguish faults from asynchrony. Why, when I'm designing an algorithm, should I think about that? So we were looking at a computational model that will treat faults and asynchrony equally. It will model them by an adversarial environment. And we were like, we want the simplest programming language possible that will enable automated verification, and synchronous programming languages are excellent for that. So we wanted to leverage as much as possible from that without paying the price of having slow implementations. So we found in the literature what is called communication close rounds. So when you work in rounds, So when you work in rounds, you structure your program. But instead of thinking what one process does as an individual, very selfish, you are going to think, what do I want a group of processes to achieve? And you can have, inside of a group, each process is going to have its role inside of each phase. But then you are going to think about your computation in terms of these milestones, in terms of these rounds. And this is how you're going to structure it. Communication close means that whatever messages you send within a round, they are going to be received or not. But for sure, between two rounds, you do not transport messages. This is very important because for verification, it will mean we will not have buffers. Well, so far, what did I tell you? I didn't separate anything. I just put rounds, right? I just said, okay, structure your computation differently. Instead of thinking of what one process has to do from the beginning to the end, put some bars. Well, that's my slide. So we looked further in the literature and we found this model that's called the herd-of model. And what it does, it's really separating the communication, the network properties from the algorithm. And the way it's doing this, it's introducing a non-deterministic variable. That's under the control of the environment. Typically in verification, we have history variables. You can see this like sometimes for concurrent verification, you use prophecy variables. In some sense, this one, you can think about it as a prophecy variable, but it's more like the type of variable that when you code, you say, I want this from the network. It doesn't mean that your network is going to give it to you. You just say what you want. So here, for example, if I'm the leader and I'm implementing, I'm implementing what the leader will do in case of an acknowledgement, it will just say, if I receive n over 2 n messages, then I'm going to modify my local state. If not, I don't do anything. Okay, so using this HO variable, this HO variable is going to determine the set of received messages. So everybody is going to send them. And then this magical variable that models what the environment is doing, how many messages it's going to drop, how many it's going to deliver, this is what is going to determine the set of delivered messages, the mailbox. Now, all the network assumptions, you can state them over this auxiliary variable called herd-of, over this prophecy variable. For example, if you really need all your messages to be delivered in every round, if they are not delivered, you're going to have a buggy computation, then you're going to state a very nice temporal logical formula that is going to guard the execution of this model, and they are saying, okay, you are not going to switch rounds until all your messages are going to be delivered. How you implement this, it's a separate issue. So the executions, in this computational model, the computation proceeds in rounds. There are no messages sent between rounds. Every round has, every process uses this HO variable to say what it wants from the network and how it updates its state in case it received that from the network. And if the algorithm makes what we call safety assumptions, has really strong requirements for safety, then it's going to say things like, in every round I want to hear from the leader. Or if it's something like Paxos, then it's going to have only liveness assumptions, and it's going to say things like, eventually I want everybody to hear from the leader. Okay, so what did we do with this? So far I told you we have replicated implementation, state machine implementation. Yes?
I'm a little confused. It seems like we can say things with these HO variables that are unimplementable.
Yes.
So
Yeah.
how is that going to be done?
So the predicate, you have to implement it as well. So for certain predicates, we will have implementations. For certain, I don't know, you know. You can have, like, if you have no predicate, for example, you are having a completely asynchronous network with faults. You can only restrict, basically, the only way to restrict your network is to impose constraints on this HO variable. So, okay, we have the implementations and we have this computational model. Well, one way we could do about it would have been to try to apply this model on the existing implementation. This is a very, very complicated task, to be very honest with you. And it requires a lot of work, hours of work. So then what did we do? We were like, can we execute this model? If we execute this model and if we can verify it, then we are winning. Modulo the correctness of the runtime, we have a verified implementation. So this is what we did. We took this programming abstraction or this computational model, we wrapped it up into a domain-specific language, we implemented a runtime for it, we implemented a verifier for the high-level computational model, we are verifying high-level implementations in PSync, and modulo the correctness of the compiler, we get a verified implementation. So that was our take. And now I'm going to bother you with a few details about, without giving you too many, about how this goes and how far we could push it. So, okay, you know, we have programs, we have rounds, they have a send phase, they have a communication predicate. Sometimes they are true, there are no requirements. Sometimes there are liveness properties, sometimes there are safety properties. And we have, the update phase. Now, the execution, these 3 rounds, for example, are executed in a loop. If we look at ZAB and ViewStamp, then they do have safety predicates. This implementation actually blocks in case the leader doesn't hear from everybody. While Paxos, and what we believe is this is why it got so famous, actually you can run it safely on any network. You need your network to provide only for liveness. But if your network provides, the other ones like ZAB and ViewStamp might be more efficient. Okay, so here is just like with the domain-specific language, we embedded it in Scala. This is part of Paxos to show you that there is also computation within the round, within the update part. So here in occurrence, there's a max computed, the maximal value among all the received ones. Other algorithms are going to compute the longest prefix. So they are going to receive sequences, and they're going to compute the longest sequence. There's minimal most often received. There are various other computations. So why am I saying this? Is because it really makes sense, this decoupling, because nodes sometimes they do make heavy computation, which is completely disconnected from the network assumptions. And in this part, in the update part of every round, you're just focusing on what the node is implementing locally. Okay, so next I'm going to move on and give you a few details about the runtime. So we have a round-based system. How do we implement rounds? Well, let's take the first case. We don't have any communication predicate. We need make assumptions for the network just for liveness, not for safety. Well, we are going to have the send and receive that are defined in the domain-specific language. And we are going to run the code over all replicas completely asynchronously. We are going to fix timeouts, how long we run, and these ones we determine empirically. We increase them, we decrease them as needed. We accumulate messages, how many are delivered until this timeout. If we receive messages from previous rounds, we discard them. We do some catch-up as well, in case we receive messages from future rounds. So now we are in a completely asynchronous system. Basically, we just like run them up to a timeout without doing any synchronization between the two of them, between all of them, actually. And this is roughly, like in a nutshell, our runtime implementation and our round switch. And if you do not have safety predicates, you do not need to do more. If you have safety predicates, then you can't switch around unless your predicate is satisfied. So then you are going to use the implementation that you have for your safety predicate. Otherwise, your implementation is unsafe. And maybe here is a good moment to say that, no, not here, later. So yeah, so this abstraction has a name. It's called partial synchrony. It's something that lies in between synchrony and asynchrony, and I think it's the most natural thing you can assume. Because, right, this is your network. If your network were always asynchronously, you would never reach, you are always going to diverge. You are never going to be able to solve consensus or any strong consistency problem. So if your network needs to go from time to time to some good periods, the green ones, where your network assumptions are satisfied. Your network is synchronous, your processes do not crash, there's not so much contention, your messages get delivered, so on and so forth. So then on the runtime execution, so if you make this assumption about the network that is not always asynchronous, that it goes through, periodically through good periods of time, then all you need to show to compute is the length of that period of time, such that, you have your system going asynchronously, and then when it goes to your synchronous phase, your timeout has the right value not to miss it. Because if your timeout is too short, then you don't receive enough messages, and if your timeout is too long, then you are just waiting too long and you are very slow. So what did we show? We showed that this runtime is correct. And what does it mean that it's correct? It means that a client will not observe any difference from a high-level PSync implementation and its runtime executions. So if you take the set of traces of these two semantics, any client that's commutative, I'm going to explain that in a second, it's going to see the same set of observable states. It's a very classic thing to prove about compiler correctness. The client is commutative. It means that all communication happens through the services. Okay, so this is it about the correctness, and probably it was the right moment to say. So maybe like Zab and ViewStem, they both use communication predicates, and what we have done, we have derived an implementation for those predicates by looking at the implementation of these actual systems. And what we are doing it now is we are plugging it into our generic framework, to compare the throughputs. While Paxos doesn't have a safety predicate, so when we run it, we can do this, maybe it will look naive, but it's not that naive. We can run it using this very simplified round switch, and we just have to assume that the network goes eventually through good periods of time, because it's a liveness property. Yes? Implementation of the predicate, it's not, it's a check if it's a safety predicate, but if it's not, if the check fails, then you need to define an implementation that is going to ensure it. So for example, you are not going to do like, if your predicate says the leader needs to receive n messages. You can check it, right? You count how many it received and it said it failed. When you implement it, you're going to stop. You're not going to do a round switch, and you're going to write a code that is going to force everybody else, for example, to send the messages to the leader, and if the leader doesn't convince them, then it's just going to commit suicide. So this is a very concrete implementation. When a new leader is going to be elected, that one is going to have it's going to be the leader, and it's going to have the support of everybody else. Oh, sorry. So now I'm switching to the verification part. So the round structure, it's incredible because it simplifies the invariants. In a nutshell, that's about it. I can tell you there are no, but why the invariants are simpler. We don't need to talk about the buffers. We don't need to talk about messages in flight. We don't need to talk about interleavings. It's very like the rounds give a very abstract notion of time. So then the invariants are just simpler. And this is not little. Everybody that worked with invariants, when they try to come up with them, they are not obvious, not even for an expert. So imagine for a static analyzer. So far, we have developed a verification engine that's based on deductive verification. So we annotate the code with invariants, we generate verification conditions, and we use a semidecision procedure to discard or not these verification conditions. We do safety and liveness because, safety we do it like usual with invariants. And liveness, you have these communication predicates, and when the communication predicate happens, it's basically an enriched transition. So if you have, for liveness, you typically have one predicate, it holds, you conjunct it with your whatever transition relation your round has, and typically you get a strengthened invariant. If you need your communication predicate to hold only once, then you're going to apply it only once, and then you're going to check that your liveness property is implied by the stronger invariant you get. If you have communication predicates that need to happen several times, then we are using something like variant functions, and we are mimicking a little bit the verification. We are just extending the standard variant function verification to reduce it to safety checks. And this is what is very, very nice about this model as well. So just to give you an example that they are simpler, this is an invariant for Paxos. For one instance of Paxos, so I did not put the entire log and the entire indexes. So it basically has two disjuncts. Either there's the commit message has been sent, roughly. I'm just putting it into, this is the actual invariant, so I'm translating it into what I've explained. Either one process has received the commit message, or either no process has received the commit message, so the leader doesn't know it has a quorum, or there is a majority of processes that already have received the commit value, the value, not the commit, the future commit value. So this is just to show you that it's a very, very simple, like lengthwise invariant. However, technically, it's involved. It has universal quantifiers. It has cardinality constraints, right? There's a majority here on an n over 2 over a set comprehension. It has all this beautiful stuff that typically leads to undecidability. We took a very classic approach and defined, in this case, a semidecision procedure to discard our verification conditions. We have identified a satisfiable fragment of it, and this is how we carry on the verification. So about the verification, so what's the entire chain? So we have the main theorem says that a client cannot, once you have verified the specification against a PESync implementation, so this round one, a client cannot distinguish between the traces in your specification and the traces that are actually executed at runtime. This doesn't hold in general for all specifications, because you can easily think about synchronous property, like everybody is in the same round, right? I can prove this easily in the synchronous world, but when I'm going to execute it, they are not going to be at the same round, so this property doesn't hold anymore. But we have identified a class of properties, and strong consistency is among them, that are transportable from the synchronous to the asynchronous world. So the runtime preserves them. Okay. One question that we are often asked, who uses rounds? Well, many algorithms use rounds. Whether they are stated directly in rounds or not, they can be put into a round form. I have like a few examples of consensus algorithm. I have some examples of case-set agreement. So case-set consensus means everybody agrees on one value. Case-set means everybody agrees on k values. More famous examples are generalized Paxos, which it is given in rounds. So there are some rounds in the text, but it's a completely asynchronous description of it. Well, it turns out we can put it in this nice programming abstraction without introducing more messages, without introducing extra communication or more memory or God knows what else you could imagine. We can put ZAB and viewStamp as well in this programming abstraction. And again, preserving their main features. And this is very important because we really try to preserve. So for example, for viewStamp and ZAB, their idea is that you are going to keep the leader alive as long as it's active. Once it's crashed, you're going to change it. While Paxos allows even multiple leaders to exist in the same time. So these were the properties that we want to capture with our abstraction, and we are happy that we managed to do it. In terms of code size, we are, with those that have a verification engine, we have a much more succinct representation. I mean, TLA has a more succinct representation, but it's just a specification language. Or this Talgo, which is the same, it's executable but has no verification engine. And in terms of the performance and the verification, we have for now only the implementation of Paxos, and it's a variant where for one instance of for one entry of the log, if you want, you run Paxos, and then you do this iteratively. It's not the most efficient one or the most optimized one, but it was the one that we could handle before introducing the safety communication predicates. And we compared it against dedicated implementations of Paxos, and our throughput is not so bad. It's only 3 times smaller than egalitarian Paxos, which is, at the time at least, it was the most efficient implementation. And we were happy because it is a quite, it's a general purpose runtime, so it's not triggered for this particular example. And in terms of verification, we did the deductive verification of the Paxos one instance definition, PSync implementation, and we played with another one. It's called 1/3 rule. It sends a lot more messages than Paxos, but has very interesting verification conditions. And with that, I will conclude. Yes.
What's the bottleneck for your system? Do you know?
Can you say it one more time?
The bottleneck for your system?
The bottleneck? In which terms?
What is 1/3? Where is?
Oh, it's okay in that sense. So it's a general implementation. So we allocate memory. It's like one allocation once. It's there's a lot of memory allocation and a lot of memory management that is not optimized at all. Like you terminate, you free your resources. That is really done a little bit more general, not specific to Sometimes you can improve in that sense and free sooner your resources, and all that adds up. All those checks and all that adds up. And also, it's not the most.
It's not that you're requesting these in terms of these routes. It's just unoptimized.
No, it's an unoptimized implementation. No. So what we try really to send the same number of messages. We play with the timeouts such that it's as good as we can. Maybe we didn't get the best timeout. Yeah. Also, I have to say, so I have to be very honest. Comparing these implementations is very difficult. So this basically is a comparison with respect to the numbers that they have given in the paper. A real comparison would assume really implementing all these algorithms and really comparing them, and this is very, very difficult. It's another one of the problems we have with our experiments, and I guess we are not the only ones. But well, with that, I will conclude. And what are we doing here? We are being lazy, you can say. We don't want to take sequential things and try to push them as much as possible. We are trying to be smart or clever. We don't know how far we can push this abstraction. We saw that it works for strong consistency. So we saw that it works for like pretty useful algorithms like ZAB and Paxos. Now, if you ask me beyond that, I will tell you my honest answer is I don't know. There's still, there's still a bit of work until we have like a really good implementation of these ones. There's the limitation of like the specifications, which specifications can be transported, like once you have proved them in this round system, they are going to be preserved by a runtime. So now we do have what we call local specifications or closed down indistinguishability. There are different ways we could call them, but like how large is this class? That we don't know either. But what we have hope for is that given the fact that these invariants are simpler, that we are going to be able to design abstract domains that are going to generate them. Actually, they are not that far off from what it exists now in the sequential world. And since we have this runtime that produces reasonable implementations, we are going to keep on pursuing this quest and see how far we get. And with that, I thank you.
Okay, there was already some questions, but any other questions? Yep.
So is it possible to apply a psync in order to produce verification of algorithms that obey other message passing patterns, such as reactive or publisher subscriber and that kind of stuff? Have you looked into something like that?
I did not look into those, so I just didn't look into them. The only ones we looked into are like agreement properties, like lattice agreement, k-set, consensus, this kind of things. The people that introduced the model, they claim it's pretty general, but I'm not going to launch myself into saying anything that I have not explored myself.
But the limitations come from the DSL or from the model. So how would you explain where the boundaries are?
So for me, that's a good question. So one limitation is the fundamental one that says how many programs can you represent in rounds. And even if you go to the system, not the systems, so the algorithms community, and you talk with those people, that they are going to tell you, we don't know, communication closed rounds, how much can we push into this? So that's one fundamental limitation already of the communication closed model. Question mark rather than limitation. Now for the HO model, I don't know. It can model any asynchronous system basically. That HO variable, if you leave it unconstrained, you can write whatever you write in an asynchronous system. But then it's not of any use. So the question is not what it can model, it's also like what it can model in a useful way.
There's a bunch of new systems where the network is providing stronger guarantees than a typical network. Ordering as a built-in primitive. The gun are actually looking at like. I'm curious if you could compile your HO assumptions into.
So let me give it a different spin. Let me tell you that, so the nice part of this communication predicates is that you don't have to stick with one implementation of it. So if your network has so ZAB, for example, has a very strong communication predicate, a safety one, that comes with a very efficient implementation that is designed for really the worst network, asynchronous network you can imagine. Now, if you run it, so it does all the recovery, it goes for a quorum, it does the recovery. It's a very involved implementation of just this predicate. Now, if you run it on a better network, you might come up with a predicate, with a nicer implementation of your predicate. So the predicate itself can be sometimes implemented in the language, in psync as well.
That was my second question. Have you thought about layering these things?
So we are layering them. So that's I did not talk about that, but we have to layer them. Otherwise, there's no. So yeah, I'm gonna look into those and see how. This is the whole quest, right? Finding as many case studies we can to see how much this model can bring to the community.